Okay, moving into module 5. Now we're actually getting into like some of the really exciting stuff. So this this is where we're talking about image transformations. This is the math side of remote sensing. Not that anything else that I have talked about hasn't included math, but this is even more so math. So we have all kinds of stuff that happens with our bands. So our bands can be very highly correlated, especially with the visible light spectrum. So anything that reflects highly blue tends to actually reflect a bit of red and a bit of green as well. So if I increase my blue reflection, I end up with increasing my red and my green as well. So it just, because of that, we need to find ways to actually pull out the actual patterns, pull out the information, reduce maybe the memory that we're using on our computers. There is a lot that goes into this. So what and then what we're trying to do is like get numbers. We're trying to say, okay, how can we actually do math? How can we make decisions later based on mathematics? Can I get values that are necessary for my particular project? Do I know how old the trees are in this area? Can I use them for logging? Can I use this particular crop, and can I calculate what the yield is going to be based on what it looks like right now? If I don't have numbers, I can't do that. So this is where image transformations come into play. And again, each of them have their own component to them, but they have their own component. They have their own challenges and advantages and disadvantages. And so just as we go through this, we'll talk about how the transformation impacts the particular applications and some of the results from it as well. And yeah, so we'll continue just going into the objectives here. So objective 5.1 is create a vegetation index image and a soil index image. So we're going to talk specifically about vegetation indices at the moment. This one is based on digital brightness. So how much energy is coming back. Often you'll see it in digital numbers, but the actual, if you're going to calculate like biomass, you need to switch over to physical units. But usually you would have had to do your radiometric correction first before you can do any of this stuff, right? So this is the processing step, right? So we have pre-processing, processing, post-processing, and presentation. We're now talking about the processing step here. We've moved out of the pre-processing. So here I'm trying to actually make some measurements with vegetation indices and biomass or vigor. So vigor is how healthy that vegetation is, and vegetation indices are a really good indication of how good that vegetation is. So we use different values, and that can be from the bands, or it can be spatially, or it can be frequency. Could be correlation values. So that's what I mean by special values. So we're going to take all kinds of different, we're going to look at the information in many different ways that comes from one single satellite image, looking at all the different bands at the same time, or just single like band, using each band one at a time. Some of these look at one pixel at a time. Some of them look at the whole image all at one time. And so, but the indices themselves are pixel by pixel. So all of these indices go back to the idea that if the index result is high, then it means it's got healthy vegetation. If it's low, it has not healthy vegetation. So the first one is a band ratio. This one is the simplest thing that you can do. You can say, I want to look at one band versus the other. So here, if we say near infrared over red, then if it's healthy, we know that the mesophyll reflects near infrared and the chlorophyll absorbs red for photosynthesis. And so therefore, if it is a high value, we know that it's healthy. If it is a low value, then it is not healthy. So it's not really a great mathematical formula to actually do anything with other than just to compare. You'll also see scatter plots are really good ways of examining band ratios. This is like, where do they group together, and where is the near infrared high and low. So you can look almost at more individual pixels just in terms of like the relationship between near infrared and red. So that's possible as well. But the band ratio, if you're actually going to create a new image with band ratios, it looks at it individual pixel by pixel, and then you can identify, oh, this area of my crop is not doing very well, just based on this quick calculation, and it takes no time at all to do. You can also use green and red, but it's really not as effective. So the green, it's because if you go back to those spectral signatures that we looked at, where the green, it kind of bumps up a little bit for healthy vegetation, and then it goes down for the red, and then it goes back up. You can definitely use it. There's going to be a little bit of a ratio there, but it's really not as effective as the near infrared because it is just that much more reflection that happens with near infrared. The second kind of vegetation index is known as a normalized difference vegetation index. This is the most common one. So you're going to see NDVI pretty much everywhere. If you do any like research reading, like for research papers, you're going to find NDVI. If you go online and you talk about vegetation, they're going to talk about NDVI. So NDVI is kind of like the gold standard for measuring vegetation. What it does is it gets rid of that weird issue of value that you have if you don't normalize. So, for example, in the band ratio, if my near infrared has a value of 10 and my red has a value of 1, my ratio is 10. If I have a near infrared value of 100 and my red is 10, my answer is 10. So the answer is exactly the same for the band ratio. And so when you do that, now if you have a near infrared reflection of 10 on the digital numbers, that means that it's not doing that well. The near infrared is pretty low, but I can't tell that from a band ratio. Where here with the NDVI, I can tell that because I'm adding and subtracting those values together. So this normalized difference, this normalization, actually constrains my result between -1 and 1. So it's all decimals, and so those decimal values will allow me, and with the addition of the negative, allows me to really identify what is considered healthy and what is not. So here's an example of numbers, what numbers could possibly mean. So a cloud is generally going to be a -1, and it means the near infrared has to be 0. So it means 0 reflection back whatsoever with near infrared. So it really, but we need to have red reflection. So what would that be? Well, clouds clouds are made of water. Water absorbs near infrared. And red is a visible light, and clouds reflect visible light very well. So it's got to be a cloud at -1. If it is 0, we end up with water, right? Because near infrared is going to be 0, and then the red is going to be also very low. Because remember, looking at that little chart, for the water, it's very low values, and at the red, it's kind of where it starts like disappearing, right, in the spectral signature. So at 0, everything is 0 except for like red might be just a little bit up. You can't really truly get a perfect 0 with this equation because if you do, then you're dividing by 0, so it doesn't work very well. But it gives you that general idea. NIR has to equal R. Then we have healthy vegetation. So let's look at a +1. That means that red has to be 0. So it means that photosynthesis is perfect, which is unlikely that you're going to get something like that. But if you were to get a +1, you know that the near infrared is being reflected perfectly and the red is being absorbed perfectly. So that would be very, very healthy vegetation in that case. This one does have a nonlinear relationship with the leaf area index, and that's looking at how big my leaves are on a tree. So that's always an indication of the healthiness of the tree. And also with the biomass, it has a nonlinear relationship with that. So I can calculate how much vegetation is there, which is helpful for both logging and for agriculture. And then there's other measures as well, but it's still a nonlinear relationship, so there's always iterations that happen. And but this particular measure is incredibly important in any vegetation application. So there is another type of vegetation index, and that is the perpendicular vegetation index. It's PVI is what I call it. So this one uses scatter plots. So you can see here's a scatter plot. I just draw blobs to show where, because there's a lot of pixels. So all the pixels kind of fall in here. And this is a very classic looking near infrared versus red chart for when you have vegetation and like just kind of a variety of stuff going on. So we have this line through here, and that is called the soil line. And so anything kind of around that is usually soil. If it's on the lower side, it's usually wet soil or like a mineral type of soil. And then anything that's like on the line is following the soil. Now it says here the B is the wet soil, so because it's getting close to water. So, excuse me, so water would be low in your infrared and red, so that would be the pixels down here. So B is falling into the wet soil situation, and C is the really dry, like sandy almost soil that falls up there. So if we take this, this particular scatter plot and we want to apply it here. Now we have the soil and the near infrared. So we're going to go down here. I'm going to talk about this here. We have soil and vegetation. That's what S stands for and V stands for. So when we look at this chart here, we're going to have my soil value, which is what is on the actual line. And then we're going to have the vegetation value, which is also on the line, is based on the red. So this is red on the bottom and near infrared up here. I will show, I'll try to use my mouse as much as I can here to try to describe this. It really is an intersection. That's all it works out to be. It's like, where does it intersect on this line? And that's what it comes down to. So we use the PVI when pixels are less than 30% vegetation. So this is really helpful when you're dealing with like rocky areas or sandy areas, urban areas, as you often have pixels with less than 30% vegetation. So it can help reduce soil brightness. So what ends up happening is you end up with a lot of soil contributing to the pixel value. And so we're trying to actually remove that this soil line, anything on that soil line, we're trying to get rid of it. So then it reduces down that value. So then we end up with just vegetation in the pixel, so in our final result. So here we calculate the 90-degree intersection between the soil line and the location on the graph, right? So intersection. So here's X. This is the point that I'm at. I'm going to draw a perpendicular line to my soil line. And then I'm going to calculate the Euclidean distance to the soil line. So my PVI value is the Euclidean distance. So we have, so if we take this and put this here, so the we have this S minus R, so, or sorry, S minus R, S minus V. So we have the soil point and the vegetation point. Ignore these little circles here. So here, this X will have my vegetation point, right? So that's my vegetation point in the near infrared. And I go down here, and that is my vegetation point for this pixel. So that's what the V stands for. It's kind of the original location on the graph. And then my soil line, which is my S, so if I draw that perpendicular line down to the soil, I'm trying to I find out where that point is. So here I have my soil line, soil point in the near infrared, and then I do the same in the red. So that's what's happening there. These lines are trying to identify between like what would be considered water or really wet soil, and what would be considered moving into the medium, and then there's drier out here. So once you've got that Euclidean distance between those, because you still have to find that intersection, then you can, that's your calculated PVI. And that's what you would give your client in that case. These numbers don't necessarily translate very easily to to mathematics, but it does allow for you to reduce soil brightness so that you can increase the vegetation contribution to the spectral signature. The next one is called the Transformed Vegetation Index. That's the TVI. So this one is similar to NDVI, and it's actually almost identical. It was just because some people get really confused with negative values, and they don't really like decimals. Everybody kind of says, well, can't you just give me like a percentage of like how healthy it is, or some sort of like, actual number rather than like a weird decimal. So it depends on the client. Some of them don't really like decimals, so they ask for the TVI. But you cannot use the TVI for any values below negative 0.5. So if you do have values below negative 0.5, you have to mask them out. I'm not showing that in this class, but you apply a mask to it. It gets rid of those points, and then you can apply this TVI. Now the reason you can't use anything below, any like pixel values below 0.5 when you do the NDVI is because of this. So I have my NDVI right here in the middle. And so we're going to take this, and then we're going to add 0.5 to it. So at this point, we're expecting that's going to elevate it past the 0 mark. And then we take a square root. So it's because of this square root. So if I have like negative 0.75 for my NDVI, I'm going to end up with negative 0.25 within these brackets. And if I take the square root of a negative number, I end up with an imaginary number. So we're going to keep it real in this class. We're going to stay away from that. So don't use this with negative 0.5. But then you multiply it by 100, and you end up with your result as a TVI. Does it look any different? Maybe slightly, but not greatly. Then we have an enhanced vegetation index, which is also known as the EVI. So here we have really like there's some limitations with the previous 4 indices that I just finished talking about. So some of the benefits of this one is that it's more sensitive to changes of the biomass. So before it kind of looks at generalized data, now I'm really looking at, okay, it maybe the type of tree might have an impact. So this is a lot more sensitive to that. It also reduces atmospheric conditions. So if an atmosphere is absorbing near infrared and it's not actually getting to the sensor, even though it did get reflected from the trees or the grass or whatever, then this one helps reduce that influence. And then it also corrects for background noise. So when you have a lot of like a really thick canopy that the light can penetrate into, it can often reflect as it comes out, and as it is reflecting within itself, it ends up following different pathways, and then it takes longer for the light to go to the sensor, and then the sensor takes that and says, oh, it's part of the tree. We try to minimize a couple of these things, especially the canopy noise, in radiometric calibration, but the canopy noise here is that additional part, especially if you're dealing with tropical rainforests. So something a little bit about it is that it's more sensitive to leaf area index than NDVI. It also is really sensitive to canopy structure. So it will give us more information about what this canopy looks like. It's great for phenology, which is looking at like types of plants and like, anything about a plant itself. And it's also more sensitive to plant stress. So if a plant is starting to show signs that it is not doing well, this is going to detect it faster than any of the other previous 4. So this is a very common index used with MODIS satellite. We're not using MODIS in this class, but this is the formula that MODIS uses. And so we have our C1 and C2, which are coefficients that have been calculated either through least squares or they're given to you depending on which satellite you're using. Then we also have B, which is the blue band. We added that in. Why? Because of atmospheric conditions. Then we also have L, which is the conditions of the atmosphere as well. So we have like 2 components. And so this 2.5 does change depending on which satellite you're using. So this is just specific to the MODIS satellite. So this is, you end up with a value, and every single pixel is going to have an EVI value. It has to go through this entire formula for every single pixel in your image. This is why we reduce our images down to 2000 by 2000, because you can imagine how long this could take. If it's pretty fast, but it still can take a little while depending on the speed of your computer. Then we have another one. Now we're getting into soil adjustments. So the soil adjusted vegetation index. This is a great index for anything that has less than 40% vegetation and is in an area where there is soil. So especially like crops, right? As crops are emerging or after they've been harvested, we can take a look at this vegetation index. Not that you really want to look at vegetation after it's been harvested, but who knows? Teach their own. So we use this when the soil is also different across the image. So you saw with the Calgary images that I've been using, the Calgary image goes from like past Drumheller all the way to Banff, right? Like past Drumheller going to the east and all the way to Banff. It's a big image. It covers a lot of space. The soil in Drumheller is very different than the soil in Banff, which is also very different than the soil in like Airdrie. So because the soil is so different, I would use a SAVI, S-A-V-I, Soil Adjusted Vegetation Index, to calculate my vegetation health. So we can correct for soil brightness again. So we have, now L is representing something different. It's not atmospheric effects anymore. It's now soil brightness. It's from the exact same textbook that I pulled this out of. And then, of course, they have to use just the same letter for two different equations. So we have what looks like NDVI, and then we have the soil brightness correction factor. So if it is close to 0, there's lots of vegetation. If it is close to 1, there's no green vegetation. Okay. So that is our formula for, oh, just a sec. That should be a negative, should be -1 minus L, not a plus. You'll see that changed in your PowerPoints. So that that's the SAVI. So we're trying to correct for soil brightness. But how do we get this L? Where does that come from? So because it became trial and error, we're like, okay, well, if we keep trying, we'll eventually like match some of our observations, and then it will eventually give us the right answer. That doesn't really save a lot of time, so they decided to modify it, and so now we have the modified soil adjusted vegetation index, which is MSAVI. So MSAVI calculated L using this formula here, where S is the slope of the soil line, the little s. And then once we've calculated L, we could go back to my regular SAVI and put it in there. But when we calculate the second version, they actually like combined it all into one and then made it so that it matches the MODIS satellite. So now the MSAVI2, which is the second way of doing it, they just created this formula for MODIS. So if you are using MODIS and you want to do the MSAVI calculation, then, and it has the same benefits as the regular SAVI, then you would use this formula at the bottom here because it's already created. But if you're using Landsat, you'd have to calculate L this way, and then you would go back to the regular SAVI to do the calculation. And last but not least, good old soil. Like there's so much soil calculation in all this because vegetation and soil kind of go together. So the soil index, this one takes, it looks at green and dead vegetation. So I actually can like separate out the two rather than just saying no vegetation or there is vegetation or it's healthy or whatever. This one actually says it has a measure between green and dead and then no vegetation. So where before you saw that it was like healthy vegetation, water, and clouds, this is now taking that to like the senescent vegetation. So here we have, again, it's a normalized value, so it goes from -1 to 1. So if it has -1, there's absolutely no evidence of vegetation whatsoever. So it's all gone. It's all just soil. If we have 0, it's all senescent. It's all dead. So whatever it was that killed it, it's now done. You can't do any more. And then there's +1, which is all green vegetation. So there is no soil correction in, like, well, it's corrected, but there's no soil in the end value, and there's no evidence of like water sitting, like pooling on the ground or anything like that. So it's merely looking at vegetation leaves in this case. So SAT-V, here's the formula. We have L, which is the slope of the soil line. Again, there's an L for everything. So this would be the little s from the previous M-SAVI. But SAT-V, it's the slope of the soil line. Generally speaking, we'll say it's 0.5. But if you're looking for something that's more specific, then you'll actually have to calculate the slope of the soil line in that scatter plot to get this calculation. So that is that's our vegetation indexes. So there should be 8 of them. So we have the band ratio. We had NDVI. We had PVI. We had EVI. We had TVI. We had SAVI. We have M-SAVI, and we have SAT-V. So those are all of the vegetation indices. They also include the soil adjustments in them, especially in the last 3. And I really suggest looking up vegetation, or not vegetation, but just indices in general. So if you are doing a project on like forest fires, you can use definitely a vegetation index, but maybe you might find there's actually a forest fire index out there as well. So maybe go check that out. Maybe you are dealing with glaciers and you want to see the change in the glaciers and the ice. Guess what that means? That means that you need to find an ice index. If you were looking at like the expansion of a desert, what does that look like? And what does the soil index look like? So there are a ton of different kinds of indices out there. You just need to do the research and find it. A lot of remote sensing ends up becoming what is going to work for me, and I'm going to look it up. So that's where these indices come from. So take a look around and think about what your project is and try to come up with an index that applies best for your project. We'll get into Objective 5.2 in the next video, and I will see you then.